Record. Hello, friends.
Hello, Mr. Stone.
It's like old times. All right. Well, we gotta go over magnetism. This is for both the conceptual and the honors classes. Let's adjust that. Drop a dinosaur. All right. So first thing I want to make sure everyone got from the video is the concept of where magnets get their power. Where does the magnetism come from? All magnetism, and this was discovered by Hans Ørsted, magnetism is the result of charges moving. So if you have a charge, like an electron that is in motion, it will be generating a magnetic field, and as a magnet, it can be pushed and pulled on by other magnetic fields. If it's just sitting there in space, you got an electron that's just existing, that won't do you any magnetic good. But if it's moving like an electrical current, you will get a magnetic field. How then, well, that explains electrons moving down a wire make a magnetic field, as in Ørsted's very famous discovery, or an electromagnet. But where do you get like a permanent magnet? Like a refrigerator magnet doesn't need a battery to work. Well, there's still moving charges in it, because in every atom, there is a nucleus being orbited by a negatively charged electron. So if every atom acts to have, let's say, a magnetic field oriented like this because it has an electron going around, why do we have stuff that is not magnetic? For example, I can bring my magnetic compass, and it is attracted to the steel. You can see this, the steel in the tab that you guys like to rip off of pen caps. And there's attraction there because steel is ferromagnetic. But I bring it near to the plastic end of a pen and nothing happens. What's the difference? Well, remember from chemistry class that electrons like to exist in pairs. Even hydrogen, which only has one proton in the nucleus, still prefers to have two electrons. So if we've got one going around this way and another going around, let's say, in this direction, if this one is spinning that way and makes a north here, then spinning the other way around should give you a south there and north here. So if this north was pulling on you, this south would repel you, thus they cancel out. So that's why most things are not magnetic. However, there are three elements where this does not cancel out. The three ferromagnetic elements. Can anyone give me one of those three substances?
Cobalt.
Cobalt.
Iron.
Iron. And the last one?
Isn't it nickel, I think?
It is absolutely correct. Iron, cobalt, and nickel are three ferromagnetic elements. Anything that contains these has at least the possibility of being a permanent magnet. Different alloys, for example, the steel in the pen tab contains iron, therefore it can be magnetized by bringing it near a neighboring field. But it's not normally a magnet. Like, I can't use my pen to pick up paper clips, but I can use it to attract this compass. Why is that? That has to do with magnetic domains. let's say we've got an atom here with a magnetic north and a south in this arrangement, and then a neighboring atom just by chance happen to have the same orientation. Well, now if you're pulled on by a north, these two both pull you together, giving you effectively one bigger, stronger north and one bigger, stronger south. And the more atoms that are aligned together, the larger the domain, the more atoms that are aligned together so that you get magnetic force reinforced, the stronger a magnet will be. However, if these two are working together in this lump of crystal here, and this lump of iron has a south here and a north here, that would cancel. So this would be unmagnetized. This is what you get when you have random alignment of domains. And that's how the steel in the pin cap is normally, or the steel in a paper clip is normally, or an iron nail. Those things are not typically magnetic, but if you bring them near to a magnetic field, what it'll do, like the magnetic field coming from the magnet and the compass, these domains will line up with that field. So if the magnetic field from the compass magnet, let's say here's a north, here's a south, we always draw our magnetic fields as going from north to south. So this one is lined up with the magnetic field. So this one, if there's any neighbors that were kind of like halfway, they might join up, and this magnetic domain here grows because the neighbors that were almost about ready to turn now get a little bit of extra outside help, forcing them to turn and join this domain. So this already aligned domain will grow, and this one, which was not aligned at all, will be forced to turn and align. And now the whole thing will be magnetized. Like if we could zoom in on some portion of the steel sample. North to south, 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 north to south. So we'd have a big strong south here, a big strong north here, and it begins acting like a magnet. Permanent magnetism, anyway, is all about these aligned domains. Therefore, how do you think you might knock them out of alignment? How do you undo this in order to make something that's magnetic not magnetic?
Heat it up.
You can heat it up, because what happens when something's hot? What do the particles do? When something is like really, really heated up, what does that mean in terms of if you had an electron microscope and zoomed in on the particles, what would you see?
They spread out.
They spread out, they wiggle around, they're bouncing around. Structures that hold them together break apart and free them. So heating a magnet, and this was discovered by William Gilbert, I think. Heating a magnet will reduce its magnetic strength. Why? Because these domains get broken up by that. So another way to crack those alignments, other than heating it, might be to physically strike the magnet and just knock them out of alignment. Of course, that also works the other way around. Let's say you have something that is stubbornly unmagnetized, even though you have it near a magnetic field. For example, did you know that train tracks end up becoming magnetic over time? If you have a set of train tracks that run north to south, well, on day one, when you lay the train tracks, they are not magnetic. Day 30, still probably not magnetic. But after months and months of trains going by and shaking them, while the Earth's magnetic field slowly grows and turns those domains, over time, your train tracks, every little alignment, every time it gets shaken, those already aligned domains grow, the other ones turn, and eventually train tracks that run north to south end up being magnetized by the Earth's magnetic field. So if you happen to live near some train tracks and you can go over to them safely, then you can try taking an iron magnet and seeing if it sticks. So shaking it, if it's already magnetized, might knock loose some of those domains. If it was unmagnetized and you have a magnetic field and the thing is stubbornly not going along with it, give it a tap. A demonstration that I usually do when we're in person is to take an iron bar and a hammer, point the iron bar north to south, give it a tap, and then you can use it to pick up a paper clip. Strange but true. And that's all that magnetic domain stuff. Now, a very common kind of question that I'm strongly hinting that you might need for tomorrow's quiz on magnetism basics. Very common kind of magnet question. So you've got a north here, a south here, and it magnetizes and picks up a paper clip. If the paper clip is made into a magnet, then it must have magnetic poles. What magnetic pole must be located in this region of the paperclip?
North.
It would have to be a north. How can you tell?
Because north only attracts to south.
Right.
Opposites poles attract.
Absolutely correct, Crystal. This south is pulling on a north. That's the only way it would work. A south couldn't be pulled on by a south. They would repel. So if the north is on this end of it, then this end of the paper clip must be a south. And then if they want to really give you something to chew on, you could say, all right, but there's also a nail stuck to it, and there's like a thumbtack, and there's another paper clip, maybe like I don't know, like a fishing hook. And then you just have this long chain of items, but you just carry through the exact same process that you just did. This would have to be a north, this would have to be a south, this would have to be a north, this would have to be a south, north, south, north, south. And if you think about it, which you should, this is a science class after all. If you think about it, these have all lined up with the magnetic field lines. If we draw them as going from north to south, then this line went like this line went like this, and this line went north to south. So they all lined up. This north scared away all of the norths, so they all pointed away from it and pulled the souths toward it, or you could think of it from the south perspective, but either way. Similarly, another kind of problem that is basically the same concept of this, just dressed up differently, is to have a bar magnet surrounded by a sea of compasses. If the needle of a compass always points towards geographic north, remember, geographic north, attracting the north end of a magnet, must be a magnetic south, as I explained in that video that I imagine most of you watched. geographic south must therefore be a magnetic north. A compass needle points north, so the north is attracted to the south. The geographic south is a magnetic north, which pulls the non-pointy end. Some compasses, like mine right here, are pointy on both ends, in which case they typically color the north side red. But most of our tests are not printed in color because public schools are poor and deprived of funding. So if we are just using pointy to indicate the north end of a magnet, then this would have to point away. This would point away. This one would be pointed almost like kind of straight up, because it would be pushed away by the north and pulled toward the south. No, actually, this one would have to then be horizontal, wouldn't it? If it's pushed away from the north and pulled toward the south. And then they would dip toward the south end. And I have a bar magnet and compass to show this to you. Hang on, let me liberate this. There you go. Put the compass next to it. You see that, well, for one thing, it's very responsive to the bar magnet. South to north. And then the north is pointed directly opposite the north. I start to move it around, pointed away from the north. Away from the north. And here, it actually becomes horizontal. So the north is pushing the north away, pulling the south toward it. The south repels the south, and the north pulls the south toward it. If you did some vector drawing to indicate like directions of the forces, you would arrive at balance in this position. And then beyond this middle position, the south is the dominant thing, and you see the north pulled toward it strongly. But what this is doing is basically showing you the magnetic field lines. They go out from here. They're horizontal at this point. And boom, there you go. It even points in the same direction as the compass. So you can use a sea of compasses in order to show magnetic field lines. Or if you didn't know how to draw magnetic field lines, you could just get a bag of compasses, surround the magnet, and it would show them to you. All right, so those are some of the basics and the kind of problems that you might, hint, hint, wink, wink, see on tomorrow's quiz. You guys ready to move on to the magnet sheet? Check your answers.
Yeah.
Do it.
All right, team. Help me out. List 2 ways that magnets are like electric charges. I'll be happy if somebody can give me one. One of the 2.
Electrons. Oh,
Okay.
go for it.
No, electrons. Give me a little bit more.
Electrons flow within magnets. Like they're the ones that move.
So they are related by the action of electric charges. I'm actually going to give that kind of like the bonus position of being a 3rd way. You're completely right. But there were 2 that I thought would be more obvious, but you went for the hard one, which is impressive. So both result from the property of charge. Very nice. In terms of their behavior, can anyone think of a way that they act similarly?
I said that like the opposite charges attract.
Absolutely. So the fact that you said that there can be opposite charges, well, something that they have in common is that there's more than one type of the property. So there are two types of property, I guess it's polarity. So for electric charges, it's positive and negative. For magnetic poles, it is north and south. And this results, as you just said, in opposite poles attracting and similar poles repelling. I think there's two L's in repelling. All right, give me another behavioral similarity. So there's two types. They attract and repel. They both get caused by charged particles doing stuff. And there's another similarity. Think back to when I was rubbing balloons on people's hair in class in order to get their hair to stand on end and attract the string hanging from the ceiling. No, are you guys stumped? Remember, you can hold the space bar down to unmute yourself if you wanted to answer. All right, I'll give one last hint. They're field forces. What is it that is true about a field force that differentiates it? Come on, guys. A contact force has to be in contact, but a field force can act. Come on, guys. This is recorded.
Fields. They act through fields, like they can push their like electricity through the field. Same with magnetism.
So the action goes through the field, which means that they can push and pull without having to do what?
Touch.
There we go. Both can exert a force over a distance, and that space within that distance where that field can act, or where that force can act, is called a field. So another thing is that they are both field forces. Regions that produce magnetic forces are called magnetic
Poles.
poles. Thank you, guys. Is the following sentence cierto o falso? Every magnet, regardless of its shape, has both a north and a south pole.
True.
Absolutely true. The only way you could get like a magnetic monopole that is a north without an accompanying south would be to have like some really, really exotic situation, like extreme temperatures, or like it was the first couple of minutes after the beginning of the universe. Weird stuff that's not like the mundane physics we're concerned with. But yeah, if you think about it, if this is the alignment of the domain, well, that's north to south. You just can't have one without the other. Attract or repel, describe the effect of bringing poles listed below together. You bring a north near a north.
Repel.
Will repel.
It will absolutely repel. If you have a north near a south,
It'll attract.
absolutely. And a south near a south.
Repel.
All right. Now, when will those two souths repel more strongly? How could you make them repel, push away harder?
If they're closer together.
Absolutely. Like all field forces, they are attenuated by distance and accentuated by being close. Closer, stronger, farther away, weaker. Describe what happens when you break a bar magnet in half and then break each of the halves in half. Well, for one thing, you might end up making it weaker, but ignoring that, describe like the layout of those halves. Well, if this is arranged so that there is a north and a south, and we crack it in half, let's say that we cut it so it's a bit more of a gentle process. What would these two halves, like if I just cut them and gently bring them apart and then release them, what are they going to do?
They're going to go back together.
They will go back together because this now has a new south pole here and a new north pole here. Easy to see if you draw in all those domains. North to south, north to south. Well, it's still going north to south. This is still going north to south even after they're cut apart. Then next, you would break these in half.
Are you going over the same thing as yesterday, Mr. Stone?
Absolutely, Andy. And I'm recording it, so if you got to dip out, you won't miss too terribly much.
So I fell asleep, and that's the reason why I'm late.
Well, good morning.
Thank you.
These all still have the same alignment unless you were to twist or turn one of them. So we would have a north, a south, a north, a south, a north, a south, a north, a south. Rather like what I was showing you earlier with the long line of stuff hanging off of the bar magnet, only this is breaking that bar magnet into little pieces. But definitely keep in mind, look at how the alignment stays the same, even with more pieces. So if you wanted to put that into words, every piece will have a north and south pole. And also, I guess, the action, if you broke it as opposed to gently cutting it or something, it might end up losing a little bit of its magnetic strength. Plus, each piece is going to be a weaker magnet than they all were put together. Just fewer members in the domains. Did anyone still need to see this, or I can move on to the next page?
You can move on.
All good.
All good.
Good.
All right. Define magnetic field. James, you came really close to giving me a definition of magnetic field earlier. I think Zach did too. Would one of you like to put this in your own words for me?
I would say like the space that magnetic goes through, like the space in which it works through.
All right. The space around a magnet which the magnetic force alters. And if you are in that space, then that magnetic force acts on you. Now, this is a very kind of Einsteinian definition of it, where the idea is that the force affects space and you are in the space, therefore you are also affected, but it holds. You also earlier mentioned it in terms of vectors. We could use that as almost like a second definition. Like, this is what really happens in the real space. But on paper, what is a magnetic field? A representation of all possible force vectors of magnetic force around a magnet. All right, this one should be easy. I've mentioned this about 3,000 times. The direction of a magnetic field, by convention, we draw it as it would act on a compass or on a magnetic north. So we draw them as going from which pole to which pole?
North to south.
Absolutely. From the North Pole to the South Pole. Again, if you get that twisted, because it's 50-50, it's north to south or south to north, you might get that mixed up. It's always done as it would be on a North Pole or as you would see a compass point. So a compass needle would point away from the north and instead point to a magnetic south. Circle the letter of each statement about whether it's correct about magnetic fields. Is it correct or incorrect that where magnetic field lines are close together, the field strength is great?
True.
Yeah.
So it's correct.
That one is definitely correct. If you were to draw magnetic field lines, they spread out as you get farther from the poles. And as we said earlier, farther from the poles, it gets weaker. And therefore, this one should be pretty easy. True or false, where the magnetic field lines are far apart, the field strength is weak.
True.
True.
Very good. Where the lines are parallel, the field strength is 0.
False.
Yeah, that one's false. If you had two magnets next to each other, here's a north, here's another north. If you put a compass right here, it would kind of point like this, or actually toward that. And this one would point away, and this one would be kind of level. So you would have a magnetic field line that arcs like that. Here, it would arc like this. But in the middle, they would be going north to south straight across. Those two lines are parallel, but the strength there isn't 0. You put a compass there, it will turn. That indicates that there's at least some strength in order to provide a torque to turn the compass needle. So the field lines being parallel just indicates that the magnetic field is uniform, not that it is weak. We'll get more into uniform magnetic fields and the gang signs you can use to understand them in next week's lessons. And finally, the field strength around a magnetic pole does not vary with distance. We know that this is
False.
false. Oh man, I've been doing this one for a while. What happens when you place a magnetic compass near a bar magnet?
I guess it just moves like depending on like the needle and the which end of the magnet it's pointing at. Yes. Like it'll move to
Absolutely. The needle of the compass lines up with the bar magnet's magnetic field. Why are certain substances such as iron magnetic, but other things aren't? This is more or less the first thing we went over today.
Yeah, it's like the magnetic domains are all like in the same direction. Yeah.
Absolutely. But on a much smaller scale, like a domain implies multiple atoms. This is even smaller than that. The electron structure is aligned in a way that doesn't cancel out. Within one atom, you don't get cancellation. Not multiple atoms like a domain, just little electrons going around in their orbits are aligned in a way that does not cancel. And let's see, most substances have their electrons, you guys remember that abbreviation, right? E negative. Electrons, orbits, structured in a way, that pairing that cancels out magnetic fields they produce, except for iron, nickel, and cobalt. Their electronic structures allow and encourage magnetic fields as opposed to canceling them out. We good on this page, or do you need a moment?
I need a moment.
Okay, I'll give you a moment. While you are getting those last couple of notes, let me just say that today's Zoom meeting is brought to you by Raid Shadow Legends.
Oh yeah, Mr. Stone, I have a question.
All right, what's up?
Okay, so like I know how you were saying that like you can heat up substances to like make them unmagnetic. Could you do that for like iron, nickel, and cobalt too?
Yeah.
And, like take away the magnetism.
Absolutely. If you had a magnetic lump of iron, that's because those domains are all lined up. You heat them up, they'll bounce right out of alignment. Of course, if you heat it up enough, then you don't even get those crystals to be aligned. You just have liquid iron. But what is also interesting is that it works the other way around. If you have a really, really cold magnet, then those domains are really, really, really stuck in place. And cold substances end up, or if you took a lump of iron and made it colder, it would actually be a little bit better at maintaining its magnetic strength. Think of MRI machines. Not only do they generate heat by resistance, but also magnets just work better when they're colder. So they're actually cooled with liquid helium, because liquid nitrogen, that stuff that can make ice cream in like 5 seconds, liquid nitrogen's too warm. So you have to use liquid helium. All right, you guys ready to move on? Last page, we're almost done. What are magnetic domains? Oh man, we're hitting all the greatest hits of stuff that I've repeated too much. Who haven't I heard from in a while? Ethan, you want to get this one? Hit the space bar to unmute yourself, Ethan. Ethan, you still alive?
Yeah, I'm there. Hold up.
All right.
I got down region without a magnetic material.
All right. So it is a region within a magnetic material. But what is special about that region? Within that region of the magnetic material, there is what feature that makes it notable and makes it worth asking questions about? Anyone want to help Ethan out?
It moves in a like one direction, like a uniform direction.
Where the clusters of particles, nice, are aligned so that their magnetic fields reinforce. Is the following sentence true or false? The difference between a piece of ordinary iron and an iron magnet is the alignment of the domains.
True.
Yeah, that one's absolutely true. If it didn't have those domains lined up, it would be unmagnetized, but because they are lined up, it is magnetized. Describe what happens when the magnetic domains in an iron nail are brought near a strong magnet. Again, we talked about this not with a nail, but with a paper clip. The domains that are already in alignment will do what? Come on, guys. The domains that are already lined up with it will do what? Remember this drawing. I started it like this, and I said that the ones that were neighbors who were on the fence, and then I expanded it to indicate that what happens.
And they just like build up or like help like assist each other.
Absolutely. So that domain, as it builds up, will grow and recruit neighbors. And domains not in alignment with the bar magnet's magnetic field will do what? Well, how are you going to get it to grow if the ones that weren't in alignment don't do anything? They've got to do something.
They change alignment like if you were to put a paper clip onto another one that's already connected to a magnet, they start becoming magnetized.
Exactly. And in the same direction. So they will come into alignment. If an ordinary nail is removed from a strong magnet, the nail will lose its magnetism. Why does this happen? Now, you've probably done this before where you had a paper clip that was hanging off of like a refrigerator magnet and had another paper clip hanging off of that. And you try to pull the paper clip off without the next one falling off of it. And you've got to be extremely gentle in order for that to happen. Why? Why do you have to be so gentle with it in order to avoid losing the second paper clip?
Because it's quite similar to like moving it. The dropping, the breaking, stuff like that. It's quite similar to that.
There you go. If you give it a strong impulse, you might shake those domains out of alignment. The action of pulling it apart can shake the domains out of alignment. And or, yeah. So, and or there's another thing that could happen. The nail might just be warm, and regular thermal motion, the wiggling of warm particles in a solid, that might be enough to unmagnetize it without the help of the outside field. So, and or thermal motion wiggles, that's a scientific term, by the way, wiggles the domains out of alignment. Actually, I think the scientific term would be oscillates. How can you make, how can, as wiggles? Wiggles is a cool word now.
Yes, you can fight me for it. And we're out of the cast, so you can't get in trouble for it.
Oh, man. Let's say you got a permanent magnet. You want to make it weaker. Give me some ways to do so.
You could heat it.
Heat it.
You could melt it down to scrap.
So heat it more. Heat it.
Beat it.
If you guys manage to make all of these rhyme, that's bonus points.
Drop it.
Absolutely. And the last one, I got a story for you guys. I was looking in my stock room and I found a bag that Mr. Diaz had back there, the old physics teacher, of compasses. So an entire bag of little compasses like this. But because they were just like jostled around in a bag next to each other, over time, if you had a north just sitting near a north, they're pushing each other apart. They will torque each other's domains out of alignment. If you store a magnet improperly, like having a north near a north for a really long time, they'll push apart, and that will decrease their magnetic field strength. So storing magnets improperly with north near a north and a south near a south will over time weaken them. If you have 2 bar magnets, I have here the packaging. When you buy labeled bar magnets, they typically come in pairs in this plastic container. The proper way to store them is like that. So that this, we've got a north to south action here, a north to south action here. So this makes like a nice kind of magnetic loop. If you store them like this, we have repulsion here. That's not good, because eventually these are going to kind of start to line up away from each other, screwing up the alignment at the poles, making the magnet overall a little bit weaker. If you do have a magnet that has been made weaker by this action, what you can do is you can take another magnet and as I think William Gilbert was his name, found, you just rub it along the magnet in the direction you want it to be magnetized. That's actually how Jared Still and I last year remagnetized all those compasses. Strong neodymium magnet, figured out what its south end was, and swiped that up the needle in order to teach the compass to be aligned north to south. All right, so that's all of our magnetism packet. We do have a gizmo this week that'll help you be prepared for tomorrow's quiz. I want to go over that. A couple of you have given the gizmo a shot. I know Blake has. Has anyone else tried it?
I have.
I have.
All right. So this week's gizmo is called magnetism. Let me mess with this screen sharing thing so that I can share with you guys my screen looking at the gizmo. There. Okay, hopefully everyone can see my screen. I've got period 2 pulled up because it seems like we have the most people right now from period 2. Got a couple from period 6 though. And we're going to bring up the gizmo, launch it.
So I just think we're lucky not to have seen Alex Abels on this so far.
No comment. Actually, I haven't heard from Alex Abels. Does he have access to the internet at home?
Yes.
Well, if you hear from him or have a way to contact him, let him know to get online and do his work. All right, so we have this line. We can drag things onto it. Here I've put on a magnet north to south. If I put this magnet here, what is it that you expect to happen?
Repulsion?
Repulsion. They scoot apart. And you'll see that as they scoot apart, it also slows down a bit, indicating that as magnets are farther apart, the force
They're getting weaker.
It's getting weaker, absolutely. And if I put this here,
They're going to attract.
they attract. And if I put them farther apart at first, they start off slower and get faster as they come close together. If we take nickel and put it here, what do we expect to happen?
No. No, that's one of it is. I forget which one it is. Attraction.
It's
Maybe?
ferromagnetic, so wouldn't it attract? Slowly because of the distance. Okay.
And also, that nickel is not starting out magnetic. It becomes magnetized by being near this. So at first, it's really weakly magnetized because it is so far away. But then as it comes closer, those domains line up better and better. But if we were to try that again instead with glass, nothing happens because glass is made of silicon and oxygen.
Not made of an element that would have those qualities.
Yeah, it's not made of anything with ferromagnetic properties. So the glass is neutral and stays neutral. The iron, however, iron very famously,
Magnetized.
as you said, can be magnetized and they draw together.
Don't we actually get the word for ferro from something of iron?
Yep, I'm pretty sure the Latin for iron has something to do with ferrous, Ferrous, or whatever.
That would make sense since the on the periodic table it is Fe.
Yep.
Fe.
Absolutely. Or maybe ferric material. I don't know. My wife's a Latin teacher, not me. But notice that when we put iron on the opposite side, it gets aligned with the field anyway and still gets attracted. It's kind of like, and I had a student yesterday come up with this really good insight. It's kind of like how when you have a neutral object and bring it near to an electrically charged object, it polarizes it so that there is always attraction. Kind of similar concept with magnetism. These things that can be magnetized but start out neutral are always going to end up getting magnetized in a way that is attractive. Here we have copper. Nothing happens to copper. However, copper is a really good conductor. You put a current through copper, and then it starts to act like a magnet, but it's not permanently magnetizable. Finally, let's try this mystery element. Ooh, what's that?
That's magnetic.
It's already magnetized.
Magnetized.
And this pole right here with the RY on it must be what kind of magnetic pole?
That has to be north.
That would have to be a north. Absolutely correct. And also, I'm going to venture a guess. It is blue. It is magnetic. What element do you think this is made of if it's just a lump of one kind of metal?
Cobalt?
Cobalt?
Yep, cobalt. I'm going to remove that mystery thing. Now, this is a classic of middle school science. I have tons of iron filings in my cabinets in my classroom. If we were in a different situation, you guys would be doing this in person. But you can sprinkle little tiny shavings of iron around a bar magnet, and then you tap the table. That jostles them so that they're kind of free to move into place. You don't have friction against the table keeping them from turning. Tap it again, and they get another opportunity to line up a bit. By the third time, look what you see. That nephroid shape of a magnetic field arcing from north to south. Now notice that it is very clearly defined when you're near it, and as you get farther away, it starts to look a little bit less like the nice nephroid, and it kind of becomes a bit more nebulous, although you do still see some of the general form of the shape.
This kind of reminds me of the proton thing.
Yes, absolutely. Anytime you have two dipoles and force arcing between them, you get that this shape that's called a nephroid. If you put another magnet here, sprinkle filings, tap table, then you get, and let me show you, trace these lines across. You have north to south arcing between these two magnets. Kind of neat. But if we replace this north to south with another south, sprinkle filings, tap table, then we get a different pattern that is indicative of the repulsion. Instead of arcing from one to the other, as they approach, they begin to turn away from each other, and you get like the prayer hands emoji made out of the magnetic field lines.
There's a praying emoji?
Welcome to 2012, Andy.
Look, I don't use emojis all that much, so whenever I see a new emoji, I just don't know about them.
All right. Well, I'm actually going to leave those up there. Remember that the blue is two poles that are similar next to each other, and the pink is two opposite poles next to each other. And scroll down to number 4. Number 4, and let me, did that zoom in on it for all of you guys too?
Yeah, looks good.
All right. Good talk, team. But based on the magnetic field lines shown, what is the orientation of the mystery magnet? Well, we've got a north and a south, and we see those north to south lines arc here. And we see lines here, but we don't know what the north and south is. That's the whole point of the question, is trying to figure that out. So do these magnetic field lines between them appear to look more like the prayer hands blue, or the loop arcing between them pink.
Pray all day.
Yeah, the blue line's doing this. So that happened when we had opposite poles near each other. So if this is a south, what does that make the MY of the mystery magnet?
B.
No, like, is the MY a north or a south?
South.
It would be a south, which would make the ERY of the mystery magnet what kind of pole?
North.
So our best answer is
B.
B. All right.
That was what he was getting at when he said B.
Yeah, he just kind of skipped my question and went back to the original one. That's all right. We've gone over your magnetism packet. We have gone over this week's gizmo. You have a quiz tomorrow. I'll leave it open for, I guess, 48 hours, Friday and Saturday, to make sure that everyone gets a chance to do this gizmo beforehand so that they are as prepared as is possible. It'll be on class marker, just like the honors test from last week. For those of you who are in sixth period, it's a real simple process. You don't even need to make an account. You just click it, enter the password that I give you, and you'll enter your name. I'll have you put in your student number, your period, and you'll be able to take the quiz. Any questions?
Stone?
Yeah.
You do know about the problem of it having to be exact on word with ones you do open response with, right?
Yeah, I'm aware of that. That's why last week's one, you'll remember, was all multiple choice.
Okay.
Anybody else?
I'm all good.
All right, if you guys are all good and you feel set up for success, then let's call it here. Let me take one last look at who's still here. And remember that I recorded this, so if you missed or I guess you guys didn't miss it, but you might have missed yesterday's. Anyone who was here yesterday and wants to see this can. Anyone who dipped out today should be able to see it. And if you know someone who missed both days, then direct them to Edsby, because I'm going to post this recording. So thank you guys for participating in the recording. And I guess I'll see you guys next week. Contact me if you need a gizmo reset or if you have any trouble with class marker. And let's call it there.
Okay.
See you,
God.
Adios, team.
Thank you.
See you
Later.
all. See you, Alex.